In this demonstration, I would like to calculate the error in numerical differentiation. So I have selected a problem where f of x is sine of x and f prime of x is cosine of x. I take the point x equals pi by 4 and I will try different step sizes h, say starting from 10 raised to the power minus 3 with different small steps to 1. And I will calculate a value x plus h and the derivative at point x. And I can compare it with the exact value of the derivative, which is from cosine of x calculation. And there will be the calculation of error. So I will then plot the step size h and the error, and it is expected that in the first order methods, the numerical derivative varies linearly with the step size h. So this can be established in a simple calculation: numerical derivative minus the exact value of the derivative. So I open an Excel sheet. So let's take the x value, and I use the best value which is available from Microsoft Excel, the pi value, pi. So it returns the value of pi. Oh, it is very interesting information. Pi returns the value of pi accurate to 15 digits. So it's a double precision calculation. So pi divided by 4. And I will take different step sizes, h vector. So h is equal to 0.0001. Then a bit larger step, 0.005. Then further larger step, 0.02. Then 0.05. Then 0.02. Then 0.01. Then 0.5, then 0.2, then 0.1. So h is increasing, then 1, right? And you can go further. Right? So now the numerical derivative, as in my notation, so it is with the forward difference method. So I will calculate sine of x value. So x value is at d $1. So the value has been picked up, plus the step value minus the sine value at the reference point d1, and then divided by the h step size. That's it, right? So it is 0.707 as shown up to 3 decimal places. So there can be more decimal places. So this is to be calculated. The numerical approximation is to be calculated for all the step values, right? So the value varies as we change the step value. And now see the exact value. It is f prime. So it should be calculated from cos of d $1. So this is going to be just one single value. The exact value is like this. So this is going to be the same because all the numerical approximation is for this exact value. And now the error calculation. So the error is equal to, let's look for its size. So numerical approximation minus the exact value. So accurate to around to 10 raised to the power minus 5, right? And as the step size increases, the error tend to grow up. That's the compromise in numerical differentiation and thereby in the solution of numerical differential equations. So let's plot it and look for the equation. So I insert a graph. So I choose these data points, this chart. Okay. Select data. So add a series. So start from the h vector on x-axis and the error vector on y-axis. So we have got these points. Right? So title, error in numerical differentiation and first order numerical differentiation. Okay. So axis needs to be added. So let's look for a quick layout. Not this one. Well, this is nice. This contains the X title. So X is the step size. It is H. And on vertical axis, we have the error. This is the only series over here. Now, how do we explore the relationship between error and step size? So Microsoft Excel comes up with the regression analysis. It is available over here, trend line. So quickly, if I select the model linear, which means a straight line model between error and step size, and I look for the equation, right? And the equation is of no meaning unless I go for the r squared value on the chart, right? So it's a quick way, r squared value. And we know if the r squared value is close to 1, it means we are close to perfect fitting. So here it is 0.999984. It means the linear model between error and h, it is appropriate, right? So error varies linearly with the first order numerical differentiation approximation. Let's stop at this point. This demonstration was successful.